sample females with mustaches, whereas if you condition on mustache, you only get male faces, right, in this data set. So this is from 7 years ago. Wow, 7 years ago. Okay, but I want to highlight the main idea here, because that main idea is actually quite powerful. Observe that this simple idea extends to when latent confounders are present in your system. And observe that this simple idea extends beyond interventional distributions. You can actually do counterfactual with this. Okay? And here's my claim for that. Any deep causal model, called as DCM, any deep causal model that entails observational distribution can be used to sample from any identifiable interventional distribution. So you don't need no latence assumption, but if you have latence, some causal questions will not have unique answers. Then you cannot get to them. Okay? But if the causal effect is identifiable, theoretically speaking, then you can use DCM to sample from interventional distribution correctly after training. And the proof of this is extremely simple, okay? Proof. 1. Any identifiable P of y given to x, by definition of what identifiable means, is a fixed function of observational distribution, observational joint PV, given the causal graph. So I can write P of y given to x as some function g of P of v. DCM, the way I constructed it just now, is just another SCM. As I argued, it entails a bunch of structural equations, there's a causal order, intervention is well defined, and so on. DCM is just another SCM that entails the causal graph, the same causal graph as the true SCM. If it entails the same causal graph, that means the function that allows you to go from PV to PY given to X, that function is the same, because that's just a function of the graph. In other words, interventional distribution induced by the DCM, which let's call it QY given to X, is the same function of the joint, G of QV. So if you put things together, if PV equals QV, if you align the observational distributions, then you have Q of Y given to X as the same function G of QV, which is the same as G of PV because QV equals PV, which is nothing but P of Y given to X. So you can prove this in 4 lines. If you align distributions of a deep causal model, somehow, then any identifiable interventional distribution has to be correct through this logic, okay? So here are some takeaways of how to do this again. Given the causal graph of the system, parameterize the generative function for each observed variable with a neural network. Model the latent confounders, unobserved confounders, with some high-dimensional Gaussian noise, have sufficiently large randomness, which is easy to do. Fit, for example, you can use again, fit the joint distribution as you optimize the neural network that generate your observed variables, okay? And then any identifiable